I start looking at the parametric form of our conics. The first one, the circle, I suppose we don't do a heck of a lot with the circle in conics, but let's just have a look at its parametric form. Any point, there's our random point, x, y, we can express it in terms of the angle it makes with the centre. Instead of expressing the point as two coordinates, so you have two numbers representing the point, we're saying we have one number representing the point, but we sub it into two equations, one for the x, one for the y. Right? So remember with the parabola, it was 2at, at squared. So we had one number for the t, sub it in, got the point. So x, y, the only thing that's changing that point is the angle it makes at the centre there. So I could write it as, well, the x value over a, and that'd be constant because that's just the radius, is equal to cos theta. And so we get x equals a cos theta. And then to work out the y value, y would be a sine theta. So there's our parametrics. X equals a cos theta, y equals a sine theta. And now we can just represent the point with one number, that being the angle that radius is making with the, with the horizontal. I can prove that if you like. And it's easy enough to prove. There we are. All I've got to do is substitute it back into the equation. X squared plus y squared. And sure enough, using our trig identities, we can show, oh look, that does work out to be a squared. Right. So the ellipse must be able to be described in a similar way. Because when we think about it, the circle and the ellipse, they're very similar shapes. It's just that the radius changes in the ellipse. So how we do it with the ellipse, we use that auxiliary circle. So that theta is not going to be the angle that P makes. And that's often the mistake people make. They think it's the angle that P makes at the centre, and it's not. The way we do it is this. Here we go. I draw up a triangle that's actually going to the auxiliary circle. So I drop the vertical through the point P, join it up to the auxiliary circle, and then where it meets the auxiliary circle, join that up to the centre. That's the angle we're referring to in the parametrics. We know the equation of our circle. We also know the parametrics of our circle. So the x value, similar to what we just saw, x over a equals cos theta. So x is a cos theta. Of course, I can't use that circle for the y value. So we actually draw in the smaller circle, which has the other radius. And amazingly, well, it's not amazing actually, it'll happen every time. If I draw a horizontal from that point, it will intersect at the smaller circle. And so I can use the smaller triangle, and it'll be y over b is equal to sine theta, b being the smaller radius. And then we get y equals b sine theta. So very similar to the circle's parametrics. The difference, of course, is that the radius changes. The x value, well, assuming a is the bigger one, has the major, and the y one has the minor. But basically, we're talking the x-intercept and the y-intercept there. We can sub it into x squared on a squared, y squared on b squared. And again, using our trig identities, we can show that does work. It equals 1. All right, you may recall from our look at parametrics with the parabola, the lines we're interested in, tangents, normals, chords, those sorts of things. So let's work out the equation of the tangent and the normal. There's my formula. Well, I'm going to have to differentiate it. But I'm not going to make y the subject. I'm going to differentiate it implicitly. It'll make life a bit easier. So 2x over a squared, that's fine. Y squared on b squared, differentiate that. I can't do it with respect to x, but I can do it with respect to y. Multiply by dy dx. And of course, differentiate 1, we get 0. Remember? Chain rule, implicit differentiation, rates of change, whatever you want to call it. It's all the same idea. So dy dx ends up being minus b squared x on a squared y. So the difference with this one is we need to substitute in both the x value and the y value to work out the slope. And if you look at the shape, that makes sense. Because if all I substituted in was the x value, how does it know whether I'm on the top of the ellipse or the bottom of the ellipse to work out the slope? It needs both to work it out. Okay, we're at the point. Now, first of all, I'm going to treat it as if it's just Cartesian coordinates, so x1, y1. And so the slope would be minus b squared x1 on a squared y1. So let's work out our tangent. Point slope formula. Multiply by the denominator, which is a squared y1. We get this wonderful expression, which I've rearranged. And the way I've rearranged it is I've put everything with x and everything with y on one side. Everything else is a constant if you think about it. I mean, I know it looks like a lot of algebra, but b is a constant because it's the minor semi-axis. A is a constant, major semi-axis, and x1, y1, that's a constant because that's the particular point we're talking about. So, but that does look messy, I will concede. So I'm going to divide everything by a squared b squared, and it looks a little bit nicer because I can simplify that. Have a look at the right-hand side. x1 squared on a squared plus y1 squared on b squared. We know what that equals. Anyone want to tell me?
1.
Why is it 1? I see an alternative answer. Thank you. That's a much simpler little explanation there. P lies on the ellipse, so it must satisfy the equation. You sub x1, y1 into it, you get that it's equal to 1. So we come up with this neat little formula, but have a look at the formula and think about what the equation of the ellipse is. It's basically the same. Okay? Although, instead of doing x squared, we've gone x1 times x. Imagine that little 1's not there. Just pretend. And you've got x times x, x squared. Same with the y. Imagine that little 1's not there. Y times y, y squared. So in fact, the equation of the tangent has the same structure as the actual equation of the ellipse itself. So it makes it very easy to remember if we have to. The normal, let's see what happens there. All right, the slope now will be the negative inverse. So it's a squared y1 on b squared x1. Let's expand out and get rid of the fraction. And again, I'll move everything with an x and y on the left-hand side, everything else on the right-hand side. This time, I will divide not by the a squared b squared, but I'm going to divide by the x1, y1. And we get a squared x on x1 minus b squared y on y1 is equal to a squared minus b squared. Now, that doesn't look real neat unless you remember something. I've left it as a squared minus b squared. How else could I have written that? A squared, e squared. So the focus, squared. Because if you think about that, have a look if you don't remember. But yesterday we said a quick way of working out the eccentricity was e squared was equal to a squared minus b squared over a squared. Well, if I multiply both sides of that by a squared, I get a squared minus b squared is a squared, e squared. So actually there is a neat little relationship there. It's just not immediately obvious. So you could alternatively go a squared, e squared. I guess the reason we don't write it as a squared, e squared is because we'd have to go and work out the eccentricity. It's a lot easier just to substitute in a and b. But there's our interesting relationship, I guess, for the normal. What do they look like when we use parametric coordinates then? So it's going to be a cos theta, b sine theta. So in parametric form, the slope will now become minus b cos theta on a sine theta. It's very tempting to change that into cot theta, but don't. All right? It's much easier if you leave it as cos on sine. So let's work out the tangent. The reason it's easier is because I want to get rid of this fraction. So I'm now going to multiply by a sine theta and expand out. And that creates a sine squared theta, or an AB sine squared theta on the left-hand side. But I've also got an AB cos squared theta on the right-hand side. So I can end up using a trig identity, sine squared and cos squared. So when I move the ABs to the right-hand side, you can see it a bit more obviously there. AB sine squared plus AB cos squared is, of course, AB. Well, I'll divide everything by that AB because it would be nice to make it look a little bit like the other one where everything was equal to 1. And the sine squared plus cos squared is 1. And there's our formula in parametric form. Parametric form. Let's have a look at the normal, see what happens there. So now, turn it upside down, change the sign. Slope is now a sine theta on b cos theta. Expand out and multiply, and it's so long I couldn't fit it all on one line there. But again, I'm going to group it with the x and the y's on one side. We have a common factor of sine theta cos theta. I suppose I could change that to a half sine 2 theta, but I'm not going to. Because this will be a lot neater if I just divide everything by sine theta cos theta, and that will have the result in the right-hand side, once again, becomes a squared minus b squared, like the other one was. So we get ax on cos theta minus by on sine theta is equal to a squared minus b squared. All right, so let's just summarise all that a little bit there. So for our ellipse, the tangent, if I'm using Cartesian coordinates, will end up looking like the actual equation itself. The normal, a little bit stranger, but we got that nice little relationship on the right-hand side. A squared minus b squared, which is, of course, the same as a squared e squared. In parametric form, once again, equals 1. And there's our normal in parametric form. A lot of the time, you're going to be asked to derive it. So, it depends on the question. If it's, and we'll see this in a little while, but quarter contact questions, then we can just sort of quote it to save some time. But be prepared to derive it, such as in this question, where it says, find the equation of the tangent to this particular ellipse at the point, and we've got Cartesian coordinates in this case. So, all right, differentiate it. In this case, I've done it implicitly. I end up with minus x on 16y. But I've got some points to sub in. So 1 on 4 root 3 is my slope. And now it's just point slope formula. Point slope formula, voila, x minus 4 root 3y minus 8. It actually is rare, I must admit, that they give us nice, neat coordinates to play with. Usually it is x1, y1 and things like that. We're going to find the equation of the normal, but it's in parametric form. Now, when I did it before and I derived it, I had already worked out the slope. So I just substituted in x and y. In this question, I haven't worked out the slope. So I can do it, again, implicitly. In order to do that, we must remember, if you want to differentiate sine, you get, that's it, we get cosine. Differentiate cosine, you get minus sine. All right. So x is 2 cos theta. So dx to theta is minus 2 sine theta. Y is sine theta. So dy to theta is cos theta. And again, I can use my chain rule, implicit differentiation, rate of change, whatever you want to call it. Dy to theta times the theta x, and there's my slope, cos theta on minus 2 sine theta. And that's a little bit quicker, I think, because notice I don't have the actual equation of the ellipse here. So I don't want to waste time working out what that is, because I don't actually need it. I can find the slope this way. All right, we're talking about at the point pi on 6, so we get minus root 3 on 2. So point slope formula. But hang on, where's the point? Well, we got coordinates here. X equals 2 cos theta. Theta is pi on 6. So 2 times the cos of pi on 6. The cos of pi on 6 is root 3 on 2. Very good. But we got 2 lots of that. That explains why I substituted in. You could have cheated. Yeah, and then just look, I substituted in root 3. Let's see how we go with the y value. The y value, where is it? Ah, there it is. Oh, it's simply just the sine of theta. The sine of pi on 6. Very good. Lots quicker there. So y minus a half. Let's tidy it up. Look at that. What a beautiful looking thing. 4x minus 2 root 3y minus 3 root 3 is 0. Oh, let's have some fun. Okay, we know that y equals mx plus k. It's just our standard line. We've used k because, of course, I can't use b. We're used to seeing y equals mx plus b. Can't use b because that's going to be in the equation of my ellipse. We've used b. So just another pronumeral. But it is just our standard line. Y equals mx plus k. It's a tangent to our ellipse. Well, we're going to prove that a squared m squared plus b squared is in fact equal to k squared. I'm sure you're looking at it and go, well, of course it is. You know. Right, I'm going to do it using parametrics. There's different ways you can do this, but I'm going to do it this way. X is equal to a cos theta. So dx to theta is minus a sine theta. In case you haven't worked it out, I'm differentiating. Y equals b sine theta. Divided theta is b cos theta. So, okay, I've got my, my derivative. Now, why on earth did I do that? Because we know this line is a tangent to the ellipse. So I know that the derivative must equal m, because it's the slope of the tangent. All right, so I now have a relationship. I can link my thetas and my m's together and with a's and b's. I know m is minus b cos theta on a sine theta. Playing around with that, I've just put everything on one side. All right, I have an equation. am sine theta plus b cos theta is equal to 0. There's no mention of theta in what they're asking me to prove, though. So I'm going to need a second equation, simultaneous equations, hopefully eliminate the theta, see what we go. So there must be another piece of information that we know. And the other piece of information is this. Remember, it meets at a cos theta, b sine theta. So it means that point not only is on the ellipse, which of course we knew, but it's also on the line as well. So it must satisfy the equation of the line. So y is equal to mx plus k. But I've substituted in a cos theta, b sine theta for x and y. Playing around with that one, I now get am cos theta minus b sine theta is minus k. Now we should be able to eliminate the thetas. Going to square the first one. I'm sure that was your reaction too. Yeah, let's square the first one. Why on earth would I do that? Yeah, the answer has squares in it. I'm also dealing with trig, and a lot of my trig identities involve squares. So let's square, see what happens. We get this lovely expression. We'll square the second one as well. Oh, that's nice. Look at the middle term. 2abm sine theta cos theta and minus 2abm sine theta cos theta. Let's treat them like simultaneous equations. Let's add them. That bit will go away and magic will happen. The magic of mathematics. Add them together. Look. A squared m squared sine squared plus cos squared, which is of course b squared sine squared plus cos squared, which is of course. So we have our result. A squared m squared plus b squared is k squared. Okay. That's just one way of doing it. There are others you will see. It's a reasonably common sort of a question. All right. Let's have a look at chord of contact then. Cast your minds back to last year when we looked at parametrics and the chord of contact question. And I showed you two ways of doing it. One way where we went through a whole heap of working out, if you remember. Oh, we found the point of intersection of the line and did all this and took ages. And then there was another way I did it really quick and it felt like I hadn't done any work and you all thought I cheated. Do you remember that? Yeah. Guess which way we're going to do this? We're going to do it the way it looks like I've done no work and it looks like we're cheated. Okay. Follow me. External point. And just like any conic, you can draw two tangents from the external point. We can do it with the circle. We saw we could do it with the parabola. Yes, we can do it with the ellipse as well. We know the tangent at P has this equation. Remember, we said the equation will look like the equation of the ellipse. So I know it's going to be x1x on a squared. Notice x1, y1 is the point of contact. It's not the external point. Okay? So we know that is true. The tangent at Q, if I call the other point of contact x2, y2, will be that. We're trying to find the equation of the line PQ. T lies on both of these lines. So therefore, if I substitute them in, I must get a correct statement. So therefore, it is true that x1 x naught on a squared plus y1 y naught on b squared is equal to 1. And x2 x naught on a squared plus y2 y naught on b squared is equal to 1. We're looking for the equation of a line. Every equation of line is some constant number times x, some constant number times y, and it might have another constant number as well. Well, that's what we got. Have a look at what we got. Remember, x1, y1 is the point we would substitute in. This first one, x1, so the x, is times x naught on a squared. That is a constant, because x naught is our external point. A is fixed as well. Have a look at the y1. Y naught on b squared. Y naught is a constant. So is b squared. And amazingly, it's the same constants as the other one. Therefore, that's my line. Okay, so let's have a look at that again. The blue line, I know, is x1, x naught. When I substitute in the x1, y1, I get x1, x naught on a squared plus y1, y naught on b squared equals 1. The green line, I get x2, x naught, and so on. Okay? P and Q must lie on a line with that equation. X naught on a squared, constant times x. Y naught on b squared, constant times y. And yes, okay, it equals some other constant. That is an equation of a line. Do we agree with that? Okay. If it is the equation of PQ, then when I substitute in the coordinates of P, I must get a correct statement. When I substitute the coordinates of Q, I must get a correct statement. All right, let's substitute the coordinates of P into this. x1, y1. I will get x naught, x1 on a squared plus y naught, y1 on b squared is equal to 1. I wonder if that's correct. Yes, it is. We already worked that out. How about when I substitute x2, y2 into it? I get x naught, x2 on a squared, y naught, y2 on b squared is equal to 1. Yeah, we know that to be correct. That's our line. Done. But the beautiful thing about it is, have a look at the equation. The equation of the ellipse looks like the equation of the tangent, looks like the equation of the chord of contact. They're all the same. It just makes life so much easier. Okay? But for the chord of contact, the constant we're using is not a point on the ellipse, it's the external point, x naught, y naught. Okay? So that's got to be our line PQ, because it's 2 points that lie on the same line. Bingo. Chord of contact. Ta-da! All right, some from Patel, some from Cambridge. Sorry to confuse you out there. Cambridge.